Okay, so let's start with Bayesian inference. So once we said that we have to set up a probabilistic model, that's what I talked about, and I gave you a few details that are helpful for the following. But again, now that we have this, let's assume we have this. So how do we perform this, right? Because once we specify the metric that we want to optimize, that function is actually given. We don't have to utilize a function class. So let's start with Bayesian classifiers. They are the easiest to understand. So now my set of labels, these are the possible outcomes, omega 1, omega m. And I'm using omega because in general in classification it's not always that I convert it in +1 and -1 or 1 and 0. It could be anything, right? Something happened, right? Or a contingency on the power grid happened. And so, so in particular, this is is going to refer again to one of these outcomes. And I have two forms of uncertainty. The uncertainty for any given label of the observation, and I call this typically the likelihood in Bayesian inference jargon. And also I have uncertainty about the labels themselves before I do any experiment. This we call the prior distribution, so it's prior to the experiment. And all Bayesian inference wants is the posterior distribution, which is, again, the probability of the label given what you have observed. And this probability can be calculated according to Bayes' theorem from the likelihoods. So if I have the likelihoods, and typically the likelihood sometimes I can define through an explicit model that tells me how a contingency affects, like the fact the loss of a line affects the observation model that I have for my the state of the grid. So detection is a mapping, as we said. We have this red and black training data, and we are trying to find how to partition this space. And here, what is this plane? This plane is the plane of x, where this is x1 and x2, so I have a two-dimensional vector. And the task is more or less complicated, depending on how complicated is the way these classes separate. And you're going to have one of the mini courses is going to be about deep neural networks. So deep neural networks are very good at essentially finding very complicated boundaries, right? But again, it's sort of an approach which is based on training, so you can put it in the class of deterministic approaches, right? While for Bayesian learning, again, everything goes through this particular rule. So the division between these regions is just a function of the posterior.
Excuse me, Anna,
yes.
I have a question. So in this classification, you should know the number of classes, right?
Yes, you will have a probabilistic model, so all of the unknowns are known, right? So that's in the part of the definition of the sample space. Not only that, but you also have to have specified what we call the prior. So you have to have a sense of the uncertainty, right? This is actually, for certain things in power system, is a problem, right? Because you have very rare events. So somehow you have to assign it, otherwise the Bayesian framework doesn't work. And so in some cases, it's good to assign it based on some sense of the importance sometimes, right? Or some historical data, or things that you think are useful to provide, you know, some safety in your decision.
Actually, yesterday talked about how we can, you know, generate the data that we need in order to do the training. As you said, it's a rare event anyway. So
yes, yeah. yes. And you can also learn it. Since they're rare, you need a lot of data. Right? That's the inconvenience. And that, in a way, is the inconvenience, in a way, of Bayesian learning, right? That you have to have a model. Not only you know everything that is uncertain, but you also know in percentage how likely they are. So the Bayesian rule comes immediately with one particular detector. So this indirectly is giving you those boundaries. So the way it operates is as follows. It assigns the pattern X to the label that maximizes the posterior probability. That makes sense. This is what you think is the most likely label to give you that observation. And so this is called the maximum a posteriori probability detector. A posteriori because it's after the fact, after you observed, right? So the prior is the uncertainty that you have before you observe anything. The posterior is the uncertainty that you have afterwards. The remains after you have observed something. And you decide that the most likely one is your inference. It may be wrong because it's not probability 1. But that's the best guess you can make, right? And so you are, with this you are implicitly dividing your n-dimensional space for the pattern in regions. And again, you can manipulate this. Now here argmax means the argument that maximizes. So if you see the argument that maximizes, it doesn't mean that this function here is equal to this function. It could be or it could be not. The important thing is that the argument that maximizes that function is the same, right? So if I see equality here, I mean that the maximum of this function is the same as the maximum of this function, and so on and so forth. So the first step is simply Bayes, right? I'm using Bayes rule. The second step, though, I'm dropping out something in this ratio, in the Bayes rule, which actually doesn't change which omega I'm going to choose, because it's constant across all of them. So it's a constant factor. I can drop it. The other thing that I can do is I can take the logarithm of this product. This will split it in two components. One is what we call the log likelihood function, right? Because this we call the likelihood, and this is the log likelihood. And the other term is instead the logarithm of the prior. So you can see here that this is sort of pushing you towards things that you are convinced are more likely, but then ultimately this encodes what the observation is telling you about the label. And there is a special case in which if you really have no idea, one way of modeling this is by saying it's uniform as equal probability. So in that case, if you have m label, this will be 1 over m. So this is minus logarithm of m is logarithm of 1 over m. And we call that particular case the maximum likelihood detection. So this has a different name. Because if you think about it, you are not using the prior in this case. You are assuming you have no idea. So here are two Gaussian distributions. And here we can see that in one experiment you have a certain mean, in the other experiment you have another mean. And this particular test is actually simpler because it's very clear what you have to do with the data when you have a canonical test. So it's clear also here you have a rule, but you can sort of visualize this in n-dimensional space, while there is a very simple way of understanding what kind of rule you have when you compare only two hypotheses, right? That is this or this distribution. Now, your decision in this case is completely characterized by a threshold. So you take the value and you compare it with the threshold. If the threshold is, in the middle of the red distribution, that means that you have a very high probability that in this event you classify it instead as this other event, the green event. And if you just push it in the other direction, then you have a high probability of misclassifying the green event with the red event. And in fact, the map rule just moves it exactly in the middle, right? You have kind of the best trade-off. And you can also guess here that this will give you the smallest area in each direction. So how do you characterize? What are the things that you may care about? You may care about more certain types of misclassification rather than having a general rule. So you typically care about two types of error. One, you call it misdetection, even though this is missed detection, but you use the word miss, so this is not a young lady. Here, the probability of misdetection is the probability that you have this positive hypothesis is typically called, and this positive hypothesis, the pattern in the positive hypothesis instead falls in the region that you have defined for the zero hypothesis. And this is also 1 minus the complement of what we call the probability of detection, which could be your metric, like you want to have a high probability of detection. And the other one is the misclassification between these hypotheses that oftentimes is called the null hypothesis, right? Nothing is happening. The other one, there is an airplane or a missile, right? So you want the probability of false alarm, which is integrating this in the complementary region, typically to be small, particularly for situations where this is an alarm situation. You don't want to give a lot of false alarms. So sometimes instead of looking at probability of error or at a global metric, you look at the curves. We said that there is a trade-off between the two. You could look at the probability of false alarm versus probability of detection, and this actually curve is called the receiver operating characteristic. So you sweep your threshold, and with that you get different values of that. Now you get different values simply because your receiver, your sensors, have a certain sensitivity. If you don't have a good curve, all you have to do is to buy a different receiver, right? You can't do anything. But given what you have, you can choose which point you want to operate. Now, if you have a receiver operating characteristic that is a straight line, that means it's complete crapshoot. Basically, your observation is independent on the hypothesis. And the closer you go towards squashing yourself towards this corner, the better your receiver is. Perfect performance is when you really are matching the edges of this. Okay, so now the threshold rule is actually true in that particular Gaussian case where you have two different means, and it applied directly to the observation. But in general, there is a way of applying a threshold rule for canonical detection for all kinds of n-dimensional observations. And it goes through simply what we call the log likelihood ratio. So if you have a canonical case, you want to compare the probability of one hypothesis with the other, and you will choose the probability of the hypothesis that is more likely. Here, you are assuming these two are uniform. So the log likelihood ratio is this function, is the function that takes the ratio of these two probability of the observation given the hypothesis, and it compares it with a threshold, okay? Now, where are the priors here? There are no priors, but the priors you can interpret as simply affecting the threshold that you have. And in fact, that's what happens. So if you apply the map detector, you want the ratio of the posteriors, not the ratio of the observation given the prior. But you can simplify this and describe it as this product, the product of this likelihood ratio times the ratio of the two prior. And so you can again use the logarithm, and you see that you have the log likelihood plus the logarithm of this ratio. And what you want is this to be greater or less than 1, right? So a logarithm would be greater or less than 0, right? If it's greater, then you choose hypothesis 1. If it's less, then you choose hypothesis 0, and that's your map detector. And so you can imagine that, even for this case, you just simply, the map detector is choosing a specific threshold, but it's utilizing this likelihood ratio, which is one-dimensional, even if X is n-dimensional. So this is a beautiful case. And just to throw another name that you probably won't remember, that means that this is a sufficient statistic, right? That all the statistical information that X offers, you don't have to look at in n dimensions. You just map it in this one-dimensional quantity and make your decision, which is beautiful, very easy. So that's why, everybody loves Bayesian classification and, in general, the statistical classification tool. So, this complicated-looking expression is just simply calculating the probability of error. And the probability of error can be calculated knowing what is the probability of the two misclassifications that I mentioned before, weighting them with the probability of each hypothesis, right? So this is the average probability of error. And the interesting fact is that the map detection, as the title says, minimizes this probability of error. Okay, so if you're targeting minimum probability of error, you already know, use the map detector. You don't have to find another detector. Again, you can use the log likelihood ratio and compare it with this threshold, and that minimizes that particular metric. Now, let's look at what happens in the Gaussian case before. So the Gaussian case that I presented before, you can easily show that if the prior distribution are the same, so they have 50% probability of occurring, then the map detector is placing the threshold exactly in the middle, and this gives you the smallest error. But you may choose another criterion or another threshold, and what you're doing is essentially sweeping in one direction or the other, and then you are increasing the one misclassification against the other. And you may want to do that, as I said, because for you, certain misclassifications are more costly than others. So that's exactly what you want to do. And that's why typically Bayesian detection is presented as with the notion of Bayesian risk. Right? So Bayesian risk essentially is encoding what you consider how risky it is, a certain misclassification error. And how do you encode it? You essentially assign a function of to every decision, right? So you have a certain label, and you have a certain decision on that label. So here is when your decision on the label is equal to the actual label. Here is when the decision on the label is 1, and instead the true label is 2, and so on and so forth. Now, these are the two errors. So typically, you're not going to assign a risk to being right, right? So typically, these two guys are going to be 0. And this is then the risk that is associated to hypothesis 1, and this is the risk that is associated to hypothesis 2. Right? And notice here, these are conditional probabilities. So I haven't put there the prior probability, but the prior probabilities are useful to take the expectation of the risk. So in general, the Bayesian framework says we are trying to optimize the Bayesian risk, and one particular case, if this Bayesian risk is the probability of error, so these two guys are 1, then you get exactly, not these two guys are 1, if these two guys are 0, and these are equal, and these are 1, right, then you get a map detector. But then all of the gamut of detector you can interpret as providing a certain risk. And so the general rule of minimizing a certain choice of Bayesian risk is similar to the map detector, except that now each posterior is weighted by the corresponding error here. You assign x to hypothesis omega 1 if the risk between 1 and 2 times the posterior probability of one given x is greater than the risk of 2, 1 of making the opposite error if times the conditional probability. Okay? So here in parentheses, I'm just considering the opposite. So you decide in favor of this if this is greater than this, or you decide in favor of this if this is greater than this. And this assignment essentially is partitioning your n-dimensional space. And obviously, if you have multiple hypotheses, you have to do all these comparisons between all hypotheses, and you have a risk function which is defined for every possible pair of I and j. Okay? Now, for the canonical test, though, these are a really cute interpretation, because if you think about this rule, what it's doing is essentially, if you just want to flip the posterior, right? So here you have the posterior, right? So the posterior, I can write it as a joint divided by the probability of x, sorry. And so that probability is the same at both sides. So essentially what I'm doing here, I'm weighting the prior probability. I can interpret it as weighting it by the risk. So it's as if I am increasing or decreasing this probability because I consider the hypothesis more important. So it was kind of amplifying how likely I think that will happen. Okay, so that's a general case. When you have an hypothesis, you have to actually weight this expression by all the risks and compare it with this expression weighted by all the other risks. So the difference here that I have I here and I have j here. So these are the expression. And you can also, again, write it this way or write it with the posterior, because essentially here you're normalizing by a constant that you can remove in both sides. And so when you are then calculating the expected risk, you can calculate the risk for each label, R, and then average across all the label, and this will be the expression of the final Bayesian risk that this particular rule minimizes. Okay, so now we have talked about classification. There is actually nothing you have to know beyond what I said about classification, Bayesian classification. So all these graphical models, et cetera, are just going to be ways of doing this computation when the statistics are complicated. Nothing more, right? Because the basics are there. Same for Bayesian estimation. So the rule is very similar. The rule, you can have a map rule for this. Now, this, I wouldn't say that minimizes the probability of error. But again, it's a very intuitive rule because it says that the estimate that you make is the most likely value given what you have observed. Okay, so now, for instance, remember that I spent some time telling you about Gaussian conditional probabilities and so on and so forth. So the posterior is actually not difficult to obtain if you have jointly Gaussian model for y and x, right? Because we already calculated the parameters of the distribution, and in particular, you know that the Gaussian distribution is a nice bell, which has a single mode, which is centered around the expectation. So what is your map estimate? Is this guy, is the mean. Not only that, but that particular case is also the solution for the Gaussian case of another metric, not in general, right? That solution is only true for the Gaussian. But there is another Bayesian estimator that we are oftentimes interested in, which is the one that minimizes the square loss, right? So I'm trying to find the function that takes x and minimizes the mean square error. And this seems like a really complicated variational problem. I have to find the function. This is an integral. Oh, my God. But in fact, the solution is very elegant and simple, and the argument that proves it is as simple. I don't have the time to go through the proof, but is a few lines. And the proof tells you that the minimum mean squared error estimate given an observation of y is nothing but the conditional expectation of y given x. Okay? And also, this particular estimator is unbiased. Now, there is a lot of gibberish here. Essentially, I'm trying to calculate, so this is a substitute with the conditional expectation. Then I do my integral in two steps. I first do a conditional expectation on x, and then I do the last expectation on the particular value of x, on the marginal of x. And if I do that, I do it because then in the middle, I can substitute the first expectation with the conditional expectation. So here, these are the same. And so averaging over x, 0, gives me 0. Right? So this is an unbiased estimator of y as well. And if it is an unbiased estimator, that means that the mean squared error is equal to the conditional variance. Okay? Now, for the Gaussian case, everything is nice and simple, and the map estimator and the MMSE estimators are the same. For other cases, it's actually pretty nasty. So there are all kinds of algorithms that are focused on calculating these conditional expectations, including graphical models of various sorts. And as you can expect, losing graphical models in the Gaussian case is just giving you a way of calculating certain things recursively. But in theory, you can just sort of plug in these expressions. Now, we talked about having the statistics, and now you know kind of enough to understand Bayesian inference. But the big problem that you have to learn from the training data, the models, and you have two approaches to do that. One is that you, again, use something which is similar to having a function class, which is a parametric model. So you describe statistics like the Gaussian statistics depends on the mean and covariance. So now you have to learn the mean and covariance, and then you can do everything we said before. The other model instead is called nonparametric, and obviously there is a theory and you utilize some models, but the reason that it is nonparametric is that it seeks a function whose parameters are growing with the number of observations. It has really nice asymptotic properties, and the good part is that you don't have model mismatch because you are going to always match eventually these. But because you have a lot of parameters, you really have to be in the big data training regime. And an example that everybody understands is the difference between fitting a distribution. Here I have some observation. I say, I think these observations are Gaussian. I'm going to estimate the mean and the variance from the training data, and I have this nice smooth function, or taking the histogram, right? Where, you are going to probably reduce the classes, you reduce sort of the bins as you have more data, but you're never going to have this nice and smooth function, right? So you can imagine that the training that I need, if I make a good guess about the model, is much less than what I need for the non-parametric models. And again, to throw another type of word, there is a theory associated with non-parametric estimation, which is called reproducing kernel Hilbert spaces, that tries to do something a little bit better than the histogram, and this theory tries to prove all of these asymptotic nice results that you have. Now, when I talk about training, what am I saying? I'm saying that essentially there is a variable here, which is the state of the world, I call it, right? So basically is what defines your experiment. Then your experiment is characterized by the statistics that depend on this parameter. And you have a feature extraction here, so you probably have a model for a candidate model for the data, but then you have to convert it in the actual candidate model for the features, or you can directly have a guess for this model and learn this model. But here, only thing I have two pictures is that it is kind of useless when you are learning to distinguish between X and Y. You're trying to learn the joint statistics. So sometimes you will see that Y disappears or X disappears because I'm trying to train the statistics, right? So I'm not trying to derive the prediction of Y given X. I have this training data. I'm trying to figure out what are the statistics. And what I'm going to talk about is not the non-parametric modeling, but the parametric modeling, which is expressed here. And so that's the picture, and this is what we were doing before. Now here, if you see here, I'm just saying that these parameters are the state of the world. I'm saying I know nothing about this. Now, this is not the Bayesian thinking, because the Bayesian thinking is always, I have some model for what I'm trying to get. But in some cases, it's useful, particularly when you have parametric models, to apply this. And in some cases, you get in hot water, because fitting something with some parameter may not lead to things that are independent of that parameter. In that case, it's a real problem. So now, just like in the previous case, you oftentimes want to characterize a loss, right, in your model mismatch, right? So that you try to find the parameters and minimize some kind of loss. And so these decisions, the selection of a stochastic model and a statistical measure of success in your estimate are essentially critical. So again, here is just clarifying. You can have kind of the classical flavor, which didn't assign. It says, I have no clue what it is. This is the state of the world, and it characterizes my experiment, and I'm trying to characterize it. But you can also interpret this parametric form as really being conditioned on a set of parameters that have a prior distribution. And in this case, you're in the beautiful Bayesian statistical framework, so you can utilize actually the same approaches that we were utilizing to infer Y given X. Yeah, now you can approach this problem trying to infer theta given the training data. So the first approach, the one that has classical flavor, is only using the likelihood or log likelihood function. It's equivalent. And in this case, the best fit that you can do of a parameter could be simply maximizing the likelihood function, right? So maximizing the probability of your set of observation, right? These are all your training data given this particular parametric form, not given conditioning, but given this particular parametric form. So this is called the maximum likelihood estimator, which is the counterpart of the maximum likelihood detector. I mean, this is not, you're not detecting anything, you're just estimating a parameter, so this is going to be a continuous case. For instead the Bayesian flavor, you actually have a prior. So here, this is very busy. But again, everything Bayesian is based on the posterior, right? The posterior you can actually write as a function of the prior and the marginal. And so you can also have a map estimator for your parameters, right? Which will be based on maximizing the posterior of the set of parameters given your observations. And here you also are essentially moving your estimate compared to the maximum likelihood estimate to reflect what you think is the prior probability, right? So here you can interpret this as your log likelihood function in the Bayesian sense. This is conditioning, but still every conditional distribution changes depend on theta. And so that's how the map estimator works. Or you more generally could minimize some kind of form of loss. This could be, for instance, the mean square loss like before. And if it is a mean square loss, you already know the answer. It's going to be the conditional expectation. Now, what is the, can you ever make the maximum likelihood estimator equal to the map? In this case, no, because you cannot have a distribution which says nothing at all about the prior parameter, the parameter, sorry. So you at least have to say this parameter is uniformly distributed in a set. Otherwise, it wouldn't add up to 1, right? So you can interpret the maximum likelihood as being a relaxed version of the map detector for a uniform distribution in a set. You're just relaxing the fact that you think it belongs to a set. But other than that, unlike the maximum likelihood detection, where you can choose the uniform distribution and you have the same rule, here you don't have a real parallel in the classical flavor. So the classical flavor maximum likelihood estimator has some nice properties. Asymptotically, if theta naught is the true parameter, then it's going to be unbiased. It's not always unbiased, but it's going to be unbiased in that case. Not only that, but you can actually show a stronger form of convergence. So you have convergence in probability. It means it will go as you have a lot of independent observation really close to theta naught in the probabilistic sense. It means that the difference between this, for n large enough, the probability that this is greater than any infinitesimal positive number goes to 0. So this is called convergence in probability. We also call it efficient if it has the minimum possible mean squared error, and the maximum likelihood estimator is asymptotically efficient. So let's make some examples of model regression that leverage what we said before about Bayesian inference. And also let's look at the maximum likelihood version of these estimates. Now let me look at a model like this. I have this particular relationship between these patterns and the quantities that I want to observe, which is a linear noisy model, right? So what I observe every time is a linear combination of the entries of x with this unknown parameter theta plus what I call random noise, right? So there is some kind of perturbation with respect to that model, and this random noise is Gaussian. And let's make it zero mean. In fact, when I assume priors distribution for theta and eta, I will tend always to make the assumption that that is zero mean, because if I know the mean, I can always subtract it. So it's really kind of information I already have. So it's kind of irrelevant. Now here, if I look at the deterministic approach, I'm clearly tempted to find a least square estimation. In this case, I have to minimize this quadratic cost. This is very standard problem, has a closed form solution. You can just simply take the gradient, and you see that the gradient is minimized by this particular solution. And the reason why I don't simply put the inverse here, because in general this matrix is not square. I'm assuming that it can be tall, so that I have more observations than the number of unknowns in theta. And so this is also called the pseudo-inverse, right? It essentially projects first on the column space of x, and then takes this transformation that essentially normalizes everything. Now, what is the likelihood for a Gaussian case? So this is the term that you typically have as a factor, 1 over 2 pi to the n times the determinant of the covariance matrix. So these are all constants. We don't really care about this. We only care about the logarithm of the stuff that is in the exponent, which is another quadratic form. So it's not like this, because it has this sigma eta to the -1. But similarly, you can take the gradient, or this should be theta, and if you take the gradient, you find a solution which is a nice linear form, right? So you have a matrix F, which is your maximum likelihood solution. And this matrix is slightly different from what you had before, because now you can see that there is this sigma eta to the -1. So you need to utilize the covariance of your noise to estimate this. And in particular, this relationship just says, you know, this is actually equal to a bound that you can find for this kind of estimation. So this is the minimum variance unbiased estimator and the maximum likelihood. In this case, in this particular case, you don't have to wait for n equal infinity. This is efficient at any rate. Now let's go to the Bayesian case. Now in the Bayesian case, I need a prior, right? So I'm going to assume that the prior is Gaussian, right? And again, I have theta, which is Gaussian, with a certain covariance, which is sigma theta. And I also have a cross covariance with my observations. The model is exactly the same, except now I have a Gaussian prior for this guy. And how do I solve this problem? I use again the trick of the fact that I know the conditional random variables of conditional Gaussians are always Gaussian. So you can actually prove that y that depends in this linear fashion on theta and and y and theta are jointly Gaussian with these particular covariances. Like this is the covariance of y, right? You have assumed that theta and the noise are uncorrelated. So you have a term that depends only on theta and a term that depends only on the noise. This is the cross covariance, and this is the autocovariance. And so these fill up all these spots. And the conditional expectation here doesn't have any mean because there is no mean, right? You will typically have mu plus this matrix, y minus its mean, but I said that everything is 0, so you only find yourself with this term. And this term, if you look at the blocks that are here, looks like this. And then there is the expression of the covariance of your estimate given y, which will be this. And there is some manipulation, with some particular matrix manipulation. It's called the matrix inversion lemma. You can actually rewrite it in this simpler way. But in essence, these are the calculations we did before. The only difference is that you have to recognize how to calculate the covariance of this, the cross covariance of this and theta, and utilize this trick. So you understood. The first part was saying, how do I use Bayesian inference to do my regression or classification? Then I said, well, how do I get the model, right? And everything seems fairly smooth. I have all these rules. For other losses, it's not as simple. But there is actually complexity that comes from the probabilistic model. So even if I learn this probabilistic model, not all calculations are simple like in the Gaussian case, right? So in these cases, I have to leverage some structure that is in the distribution. For instance, I have to leverage some structure to calculate posterior, or the maximum of the posterior, or the expected value of the posterior in a more mechanical way. I have to have an algorithm.
So what if we have partial knowledge of the distribution function of the system? Not, for instance, if you're working with PV, for instance, maybe you have 1 year of data, but we know that in reality, the PV generation from 1 year to another are not exactly the same. It might be unusually cold year or hot.
Very good question. Very good question.
What should we do?
So if you think about it here, I made an assumption that I brushed through. I said all of the data have the same distribution. And that's why I can train my algorithm to do it, right? So the type of model you describe is a stochastic process that has seasonalities, right? So one approach is to essentially assume that the seasonality has a model itself. There is some kind of function of time that describe how these parameters evolve. And again, this function in time, for instance, could be a sum of sinusoids, right? And now you want to do a regression on the parameters of those. So oftentimes, or you can also parameterize as a function of time the covariance. Here I assume the covariance, I know it. What if I don't know it? What if it is a function of time? And again, so I can bring the parametric approach further than I can bring oftentimes the non-parametric approach, because the non-parametric approach really is bound to have a lot of data, right? And the other problem is oftentimes the seasonalities are not periodic. I mean, the PVs are quasi-periodic, but climate change, etc., they may not be so periodic, so I have to extrapolate. And so that's how you can deal with these issues. You have a more complicated probabilistic model, and these probabilistic models, instead of just having to do with multivariate statistics, they typically are modeled as stochastic processes. So now that we were going to move to Bayesian network, which is the meat of this course, and you will see that the theory is fairly complicated. So I don't want to lie to you. There is going to be mental gymnastic to do. But I want to excite you on the fact, this fact that graphs are increasingly used in all kinds of areas to interpret data. And here I'm trying to divide it in three really core areas, so one of which I will talk in the fourth part, which is very recent. And it kind of feeds into a new way of looking at data. But the one that the Bayesian network is really something that has been developing, in the last decade as a theory, as a more general theory, because there were Bayesian network models that were utilized before, and this is the subject we are going to cover. There is a lot of utilization of graphs also to describe the pattern that you observe, these X, right? So they are in an n-dimensional space. They lie scattered around. So oftentimes, and this is also true in clustering, so you will see most likely that in the clustering lecture, one of the way of recognizing patterns without having labels is essentially to construct this graph based on how close they are, and then just try to see in the graph what are the more close-knit communities, right? This is called spectral clustering. And so these close-knit communities are interpreted as the modes of the distribution, but they can have a pretty weird shape, right? So they don't have to be big clouds lumped around the center, right? So that will be the classic method of k-means that try to find all these lumps. Another one is trying to find this structure through a graph. So these are very interesting approaches. And I'm not going to talk about this. Also, you will have this lecture on clustering, right? So you will see that that's covered. And then I'm going to talk about this. This is kind of a new and emerging field in signal processing. It's called graph signal processing, which is trying to generalize DSP for signals that live on a graph. And so is, if you think about it, a time series is nothing but something that lives on a kind of a chain graph, right? So it's saying, okay, if instead of having this very simple structure, I now have connectivity which is arbitrary. I have neighbors on a graph. Can I generalize the notion of Fourier transforms, right? Filter, or things of this kind, right? And that's very useful because precisely because you may have random processes, sometimes you want to see these signals that evolve in time and in this spatial domain through the same kind of lenses, so sort of generalizing these as sort of a product graph of your time series graph as well as the structure, the underlying structure. So that's basically the premise in words. Some of the tasks that we described prior to this are actually computationally intractable. And so this is why in the disciplines of bioinformatics, speech recognition, machine vision, text mining, just to name a few, a lot of theoretical statistical methods have tried to utilize this particular model. Now there are some even classical models that I don't think have been applied to their full potential in power systems. We are going to have, with more data, more compelling applications of these two.